Hi there, I'm Christopher Worse, and welcome to the second video of Homework 6, going over Part 2. This one asks us for a binary mixture of benzene and toluene, write Python functions for calculating the dew temperature and pressure and bubble temperature and pressure. I just did that in Part 1, but it's behind me. We already have our calculations for that. And then it wants us to generate plots of the binary vapor or liquid equilibrium phase diagram at a constant temperature of 393 Kelvin, and then another at a constant pressure of 150 kilopascals. Now, really quickly before we go into coding, I would like to explain just an important concept. And to do that, I'm just going to draw out a really quick graph. So, for these graphs, and if you think about it, the pressure and the dew temperature and dew pressure might be slightly different because because as we know, and going back to homework 1, a triple phase exists, and then you can also have liquid and vapor together in a container and all of that. So that means that the dew temperature and pressure and the bubble temperature and pressure, the dew point and bubble point, may not be the same thing. In a pure compound, they might be, they might not be, but in a compound, they certainly don't have to be. So that means that for some pressure and for some mole fraction in the liquid and mole fraction in the vapor, that means that the graph might look like this, where down here is the, if pressure is lower, the vapor phase is down here, and the liquid phase is up here in the graph, and then somewhere around here, you have both. Now, important concept for the graphing specifically, and for making lists, and what we'll do in the thing. And let me change the your viewing so you can see this. Now that you can see this, yes. In here, sorry, I didn't change the angle. So we have vapor phase, liquid phase. Somewhere in here is a mix on a sliding scale of pressure, and the different vapor phases, the different mole fractions. Now, and it's a little common sense if you know what a mole fraction, especially in a binary mixture is, since there are two since there are two components in a purely vapor or purely liquid phase. We know that x2, the mole fraction of the second component, and usually referred to as a more volatile component, is equal to 1 minus the liquid vapor pressure, the liquid vapor mole fraction of the first component. You can also make this, of course, y2 and y1 for the vapor mole fractions, but it makes sense since x2 and x1, the mole fractions of the two components, must equal 1. And we're just going to be using that for graphing, but I want to draw that out so it makes sense. All right, so now we're able to start coding. Let me pull up a clear collaboratory script. First thing, let me just double check. So we're going to be writing plots of the binary vapor-liquid equilibrium phase diagram at a constant temperature of 393 Kelvin, and then another at a constant pressure of 150 kilopascal, or 150,000 pascals. And that's for a binary mixture of benzene and toluene. It doesn't specify what the mixture mole fractions are. I don't know, we'll say 0.3 moles benzene, 0.7 moles toluene for every 1 mole of feed that goes in. So first thing that I'm going to want to do is I have my homework 2 pulled up. I could have alternatively used homework 5, but I'm just going to want to copy and paste this from the first line of code. Again, we're going to be using this to clone a GitHub script in to get these CHE tools in, because we want to look at the properties of a few of the, specifically of benzene and toluene. So we're going to want to import sys to make sure that we have our, the first thing that we reference for CHE tools is CHE tools. We want to make sure that it's easily accessible. So sys.paths.insert. I want to say it's one content, // CHE tools. I could be wrong about that syntax, but it's not the worst thing in the world. We're also going to want to import numpy, numerical Python as np, the usual. We want to import scientific Python or from scipy.optimize. We want to import root because, as I mentioned in part 1, we're going to be using the root function to find the temperature. We also want to import, we're making figures, we're making plots, so I want to import plotly.io as PO from plotly dot, I want to say subplots? Yes, subplots, import make subplots, and then I want to, I think it's po.templates.default, nope. Could be wrong about that syntax as well, but it's not equals plotly dark underscore dark. Might get an error. Oh, I didn't get an error code. That's nice. Okay. So first thing that we're going to want to do is, per usual, if we're bringing in CHE tools, we want to look at the properties of some things. So that's going to be props. Oops. Tools. Tools.che. Oops. That's what I was missing. I want to make import tools.che as CHE. No? Yes. Okay. Good. Equals CHE dot K. Props of, and we want, it was 1 benzene, 2 toluene? Yes. Benzene and toluene. Okay. Now we're ready to kind of script out some things. And first thing that we want to do is make an array for x and y, the mole fraction of both benzene to toluene in both the liquid and vapor phase. So x is going to be equal to a numpy array of, as we said, 0.3 to 0.7. And I can, oops, really just copy and paste that. Control V, make that Y. We also want to specify our temperature, and temperature was 393 Kelvin. Yep, 393. Remember to put the dot to make it a float value, because otherwise integers can get a bit messy. And pressure, we want 150,000 or 150 E3. E3 is easier. Yeah. This will be pascals. All right. So now that we have all of that, and I actually need to bring out my notes. I should have done that earlier. I have the written down equations that we got earlier, of such as Raoult's law and all of that. Yes. So, for example, I have all of the notes from earlier. So we want to make a script for, or not a script, but a function. So define, we'll call it bubble. We'll start with the bubble pressure. And what do we want? Well, first of all, we want what components we have, because remember this depends on components. And then we want our temperature. Oops. So, oops, there. So all we want to do now is just return our value. And remember, we had the sum of the values plus the sum of the mole fraction multiplied by the saturation vapor pressure of the component. So we're going to return now. We're going to be using numpy sum for to add our two values together to make one specific value. So numpy sum of x multiplied by, and we want p dot pvap of temperature. So our our p dot pvap, remember that's our vapor pressure at the temperature. That is what we're going to be subbing in for that saturation vapor pressure in the, in the calculations that we did in part 1. So with that, I mean, we have our bubble pressure, at least the script written out, and now with that script we can write out our bubble pressure, our bubble temperature script. So again, we want x, and instead of temperature we want a constant pressure. Now we want to return, what we want to do is root something, so here, and then a temperature. So we want to root our temperature. So we're going to give a general guess of 393. And then we need to write up an equation, or function, define EQS, our equation, with given vector of unknowns, and we want t to be our first value in the vector array. Now, all we need to do now is to return the bubble temperature, bubble pressure of given, given x and given temperature, minus our guess of pressure. So if you return that, I should be just able to write EQS in here, hit Shift Enter, and be able to run that. Now let's double check to see that they work. We'll write up a bubble pressure at x and 393. Shift Enter gives an array of that means that at 393,000 or 390 Kelvin for the given mole fractions of benzene and toluene, the pressure is 298,482 pascals. Now, if we look at bubble temperature of x and what was it, 150? Actually, we were just going to use, just for this, we're just going to use T. And for this, P should be able to, the solution converged. Oh, that's nice. Oh, I do want .x, and if I were to Shift Enter this, an array, and I will also want the first value. Okay. Oh, ooh. Now, obviously this works here, but just because, for safety purposes, it doesn't change anything, but making this a one value vector makes root run easier. It's more of a safety issue. Just so I'm not getting an error anywhere down in the line, I don't want that to happen. Just to make sure everything's right, because I don't want to move on with this in case anything's wrong. Aha! This is another thing. I want this as a vector, because otherwise this doesn't run correctly. Watch. Bubble pressure changes. simply because this was only running for one specific thing. You need two. It wasn't running for benzene and toluene. It was running for something. It was perhaps just benzene, or perhaps just toluene, or something. It does affect it, and then if I here, it does change it. Okay. So now these two should, fingers crossed, be correct. Seeing no other issues. Oops. Oh, okay. Seeing no other issues, let's move on to dew pressure and dew temperature. So define dew pressure, again, given, I believe, given y and given a temperature, we want to enter. And then like the bubble pressure, we just want to return the sum of, return 1 divided by numpy sum of, and what is this? Dew point, I'm looking at my notes here. Yes, y divided by that vapor pressure. So P dot Pvap at specific temperature. All right, shift enter. No reason that that shouldn't work there. No errors. Whether or not it's we got a correct value, I'm not sure. We'll see later. I said okay. Define dew temperature now. Do T at given y and given pressure. We're going to do pretty much the same thing. Define an equation of given vector. And we're basically just going to do the same thing as the bubble temperature. T is equal to the specific vector of 0, or the first value in the vector. We're going to return the dew pressure with given y, given temperature, minus the pressure. And then we're going to return the root function of given equation with guess of, who knows, 393 as well. Should be good. Now just dot x, and we want that first value, so it's not an array. And let me double check really quickly. So dew pressure at y and t, shift enter, and then dew temperature at y and pressure, shift enter. Okay. All right. So now if you look, and as I kind of suggested with some of the graphs in the earlier thing, the bubble temperature and the dew temperature for any given pressure is different. So that means, as was suggested, that little graph is going to have this bubble in there where there's both vapor and liquid present. Cool. So we have that. Now we need to graph them out. Okay, so let's get to work on that. Okay. So now we are going to want to make some different variables for total number of moles. This could be, we're just using Z1 for variable namesake. It could be X1, it could be X or Y1. We just want number of moles of the first component. So that is going to be, specifically, we want this to kind of change over the course of our graph so we can get that correctly written up. So this is actually going to be numpy.linspace 0 to 1 with 11 spaces, and then we want Z2 as well, because to represent effectively toluene, but the second component in a binary mixture. So this would be 1 minus, and I don't need parentheses, 1 minus Z1. Okay, and then we want, finally the last variable that we want to make is we want to make a variable for our two different, an array for our two different vapor pressures. So we want, PSAT, saturation pressure. So equals p dot vape p vape, there we go, at given temperature. Okay, now that we have p set, which is an array, we can make a list. We can make different lists for our different variables. So we're going to make a list of our bubble pressure. We're going to make a list of our bubble temperature. We're going to make a list of our dew pressure, our dew temperature, and then we're going to use those lists to plot it out. So we're going to name this bubble p list is equal to, oops, and this needs to be, I think, here. Nope, sorry. Bubble p, just a variable name. Don't need that. That's just for making blank lists, like we will do in the next line. Anyways, is equal to, we want to make the list of Z1 multiplied by P sat, or saturation pressure, for our first component, and then this is going to be added to plus Z2 times P sat 1. So this is number of moles. So remember, if we look at this, our pressure is x1 plus saturation pressure plus x2 plus saturation times saturation pressure. So we've done that. So we have our bubble p list. Shift enter. And if I print it out, it has an array here. So it's got this, it's got here 130,000 pascals, 147,000, 164,000, 180,000, etc., etc., etc. It has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. It has 11 values because we picked Z1 to be linearly spaced from 0 to 1 with 11 spaces. So I can get rid of this, and I'm going to make bubble temperature list, but we don't have anything that we can make as simple as that, because I mean, bubble p list, our thing is pretty easy. Our bubble pressure is a simple sum of two products. However, this one, we have to make a blank list and then write up a little for loop for x1 for x in z1. Sorry, for x1 in z1, we want x2 to equal 1 minus x1. We also want to make a new array is equal to a numpy array. We want to use numpy array of x1 and x2. And then finally for this, we want to bubble t list dot append. We want to add, for every x1 in z1, we want to add one single variable, one single rendition. We want to add our bubble temperature equation up here. So we're going to bubble T with given x and given pressure. Okay. So we have that. Now we're able to move on to do pressure list. And this is also going to be a blank blank list, just like bubble t list. And like bubble t list, we're going to make for y1 in z1. Oops. We're going to have y2 be equal to 1 minus y1. We're going to make an array, numpy.array, for y1 and y2. And I need to add the brackets. Can't forget the brackets. Brackets. There we go. And then we want to append again. List.append. And what we want to append? Well, we want to append the dew pressure at given y and given temperature. Shift enter. And if I do the final, do it one more time for dew pressure, list is equal to blank array for y1 in z1, y2 is equal to 1 minus y1. Good. Y is equal to an array of y1 and y2. y2. And then we want to make, do t list. We want do t list dot append. We want to add for every rendition. We want to add another variable, another thing to the list, another object. So y and given pressure. Shift enter. All right. So now we have four lists: bubble pressure, bubble temperature, dew temperature. And now, if we now we can finally get to graphing. So what I'm going to do is subplots fig is equal to subplots dot just make subplots. And I want to have two, we want one row, rows equals 1. We want two columns, one for fixed pressure, one for fixed temperature. So cols equals 2. And then we want a title. So title equals t equals, or let me just subplot title. We want to make this an array. So function, we want to write a function so it could vary depending on what inputs we have for our temperature. T equals bracket out, I believe, T. K. And then F. P equals squiggly bracket, I forget what they're called. P, and then Pascals. I'll also space this out. Fingers crossed this doesn't, or it probably does. Forgot an S here. Now that that's made, if I shift enter, it still is invalid syntax because it doesn't have anything to add. I'm going to fig.add scatter of x equals, and we're going to want x equals z1, y equals, we want our we're going to use our bubble pressure first, so bubble p list, row equals 1, col equals 1, title equal, or sorry, name equals bubble p. Still having an oh, I missed the final bracket here. There we go. Hey, so we have a line. It's not finished, but we have our title. We have a graph here. We have pressure on this side. We have Z1 on the bottom. And then we have a room to make another graph over here. Now, this area here should be filled out, but I can deal with that later. We're also going to make another one for fig.add scatter. X is going to equal Z1 again. Y this time is going to be dew pressure list. Row is going to equal 1. Column is going to equal 1. Name equals, dew pressure. Shift enter. Hey, now we have names over here, and we also have a fully functional graph. So let's repeat that for the pressure. So fig.add scatter. X equals Z1 again. Y equals, get out of my way, please. No. We want our bubble temperature. Bubble T list. Row equals 1. Col equals 1. 2, sorry. And we want to name it bubble temperature. And then we're going to repeat that one more time. X equals Z1, Y equals do temperature list, row equals 1, column equals 2, so it's going to be in the second column, and then name is equal to, we're going to name it do temperature. Shift enter. All right, hey, we have 2 graphs here. They can be cleaned up. I will clean them up. And going to update our x-axes, or face our fig dot. Update x-axes. We're going to want to update our tick values. Tick vals equals numpy.linspace, because we want this to reflect Z1. So it's going to be 0 to 1, given 11 steps. And then we want to name this, name equals x, y1. Shift enter. Whoops. Uh-oh. What was our error here? Oops. Not name. Oops. Title. There we go. Now we have x and y1 down here. So our values of x and our values of y1, or actually our values of x and our values of y1. And then we want to also want to update our y-axes, so update, whoops, y-axes. We want to title them, we want to title one of them to be pressure. We want to, in pascals, want this to be row 1, column 1. And we're going to do the same thing for the other one. Update y-axes, title equals temperature. In Kelvin, row equals 1, column equals 2, so we differentiate between the two. And hey, look, we have a list of, given a specific temperature, we have our pressure on the left side here, on the y-axis, and our mole fractions on the bottom. And then given a specific pressure, we have our temperature on the y-axis and our mole fractions on the bottom. If we look at this, generate plots of the binary vapor-liquid equilibrium phase diagram at a constant temperature of, oops, that's the wrong homework. Sorry about that. 393 Kelvin and 150 kilopascals, 150,000 pascals. I'm going to get rid of this so I don't do that again. We've done it. With that being said, thank you very much for watching. I hope you have a wonderful day.